I did get 2,600,
Did you?
not much.
Yeah.
I don't know how much we got because my cat drinks out of my rain gauge.
Just
And then when the cat's not drinking out of the rain gauge, my wife is out there filling it up with water for him.
Come on.
So don't trust any of my rain measurement reports.
You guys are just not good anymore.
Yeah.
Oh, this time it made it big print. Is that from EP? You tailored? It's like it's leave my screen instead of.
I'm old myself. I know how that is.
Should I just go ahead? Is that
Yeah,
I think
we're
so.
ready to go.
Describe for the
Welcome to
audience
Weather Watch.
what today's about? Or?
Yeah, go right ahead.
So we thought it might be of interest to everybody just to try to get a little bit of the new insight into heavy rainfall events in Wisconsin. And this August, there were two spectacular ones. In fact, August 20th was kind of almost like something out of Revelation. I was in Bellingham, Washington, which is, my friend Steve Stimson coined the term city of subdued excitement. But this pall of smoke that was everywhere, and you can see that out there in the San Juans, you can't see farther than about half a mile. It was, people were subdued. Working on a sailboat, 9 days of labor, repairing things and painting, and then so you get to go one night out to Susha. It was really extremely challenging navigating. And it's odd that I don't remember really seeing the sun disk very often, but it would somehow penetrate this pall and make these amazing little big flakes of orange gold, like you want to dive in and get rich or something. But, so at the same time as this, of course, you were here. And so this is the radar for the 20th local time, and it started at about 4 o'clock, started to rain here. And perhaps we could call this rainfall event the Black Earth Creek event. It really concentrated just from various aspects. One of the main things is the general kind of, as the low track through here, you can see that sort of eyebrow shaped structure slides slowly along, and it's just kind of a nexus. But Shelley Rowe, she grew up in Milwaukee, and she's been interested in heavy rainfall events for a long time, and she now has a pretty good expertise with UW-AOS. So she started making simulations of this, which I'll show you. So here's the 3-hour precipitation estimate for that day in Cross Plains, ending at 8:30 p.m. is 8.2 inches. So my estimation is it rained really hard from about 4 to maybe 9:30, just looking at this. And here's the total amount. So this is one day precipitation. It's dated August 21st, but it's 12Z to 12Z. So 6 a.m. the 20th to 6 a.m. the 21st. So this captures the event. And it's just a bullseye right here. Yeah.
Right over your house.
So I tried to piece together the evidence. I like to go to the military bike trail, which is close to my house. This is near the Riley Tavern on Highway J. And this is the first westbound bridge. So there was so much water that filled this entire valley. This is the Sugar River Valley. I found debris, 4 feet above the level of this ramp. And all the way along the trail, you can go explore. There was so much water that at one point it was probably a mile wide and some of it flowing 20 miles an hour. These streams that would undercut bridges and lift them up, shift whole structures all around, and probably wind waves. It must have been really impressive around 9 p.m. Dangerous. See that chunk of debris at the other end there? This is kind of fun. So this is looking at it from the other side, from the west. So this stuff used to be in a marshy area about maybe 500 yards upstream, and the water just undercut the roots and as it rose and rose and rose and lofted them into these islands of vegetation, the water was flowing this high and then just kind of deposited there, kind of ran into the bridge structure and couldn't budge. And this is from the newspaper. I've been meaning to go up here, but since there was a picture in the newspaper, I don't have to. This is the Highway 14 over Black Earth Creek. You can't go there. It might take a long time to repair. I think the 232 million estimate includes the extraordinary event 1 week later, Monday the 27th, which was somewhat similar dynamically that happened in the Baraboo region. Okay, so this is a snapshot so our research interests are focused on what's happening at the top of thunderstorms. How does stratosphere-troposphere exchange go? What kind of dynamics do we have up here? And it's still kind of a mystery. In this snapshot, all right, so we're at 1800, which is noon. So this is well before it starts to rain. And so here's a positive potential vorticity anomaly. So 1 over rho d theta z times absolute vorticity. So it's positive. Rolled up PV streamer from the stratosphere, at the base of the stratosphere, is a rolled up vortex. And some people refer to these as stalactites. So they're kind of coming down from the stratosphere. When I show the movie, what happens is conduction breaks all around inside this thing. It just absolutely obliterates it. It was so extraordinary when Shelley showed me that. I thought, wow, I want to see what you people think about
What
it.
height is it?
This is at 10 kilometers altitude. So just right at the base of the stratosphere. And these are negative anomalies. So those are inertially unstable, which means if you have air in this region, it can accelerate forward, which causes local divergence and enhanced upwelling, which is the basis of the old symmetric instability theory. Here's a snapshot near the end of all this. So this is 0200 the next day, which is 8 p.m. So, well, that's right in the middle when it's raining. This is the remnant of the PV stalactite. And you can see a broad region of mild negative potential vorticity, which is mildly inertially unstable. The flow field that comes around below, and then it accelerates and then kind of runs into the geostrophic regime up in here. Yes.
How do you know what accelerates, Matt? This is a still image, but you've looked at it.
Well, okay, so this is very preliminary, and my intuition about this is that PV dipoles, it's really hard to pin them down as far as directly relating them to local precipitation. It's more of a qualitative idea that because some of one member of the PV dipole that happens at the top of a thunderstorm updraft is negative, and so it's inertially unstable. That generally facilitates overturning and rising motion and condensation and further precipitation.
Is there generally upward motion in the positive PV? And
Well,
negative PV, I mean?
let's look at that. So, so this is the last of the slide. If we want to get into it, we could also look into the storm on the 28th of August, and this is the 27th of August. At the end of it, we had 24-hour accumulations exceeding 10 inches up here in the Baraboo Range. We'll see if you want to see that case. It raises some delicate issues about location and model strategies. All right, so let's see. Yeah, we'll just go through a couple of these, and if it's taking too much time, then we won't. I think we already saw that. All right. Here's the PV without vertical motion, and isn't it extraordinary how vividly these thunderstorms just destroy the PV anomaly? It's just very rapid erosion.
This is interesting from the perspective that this storm was actually a very obvious extratropical storm. And you even saw it in the close-up in the radar, that the radar echoes were pivoting around sort of like a triple point or something. And so with still mid-summertime convection and an upper level dynamic structure that's more like an extratropical storm, maybe that's why we don't see these kind of things so often. This rapid obliteration and Swiss cheesing of this thing out of existence.
Maybe it is a late summer kind of phenomenon.
Yeah, with a clear extratropical connection, which is not common at that time of year.
Another feature about this one is there are no really robust PV dipoles per se. They're kind of very irregular, and I think I understand why. At least it's a hypothesis, which is in the center of this, such as like in the center of a hurricane, the winds are fairly weak. So thunderstorm updrafts are carrying moderate speed air into moderate speed air aloft, and so you don't create a horizontal jetlet. But in the one for the Baraboo Hills, these PV dipoles are much more evident, and they're created by, if the mid and upper troposphere is moving very fast compared to the base of the stratosphere, a very narrow updraft with fast moving horizontal air punching into it at a short horizontal scale, and you create a little jetlet relative to the ambient air, and that means that you have a dipole in vorticity. So a dipole in vorticity is a signature of a very rapidly moving horizontal air that's punched into the base of the stratosphere. Whereas this air isn't moving very rapidly horizontally, so there's no organization of P dipoles per se.
Does a dipole suggest a solitary wave at the base of the stratosphere?
They're always they're intimately related to gravity wave formation. So the downdraft, it extends into the stratosphere as a negative W prime tilted maximum.
But could it be kind of a solitary wave moving along the tropopause?
It could be. People still talk about those, don't they? These little sort of odd entities that propagate along the tropopause that are, yeah, Sato and Dunkerton had something like that.
Or I wonder if it's a wave forced by the convective heating that kind of just propagates along the tropopause.
Oh, what the PV dipole is?
Yeah.
Oh, it's deeply connected. So here, this will make it more clear. So these are, these little black blobs are the 3 meter per second updraft isosurface. So maybe I should stop it. How about it? Right there when it's 0200, so that's 8 p.m. raining pretty hard. But this is an updraft here, negative PV. So what happens is you connect the boundary layer all the way with the stratosphere. You have an updraft, and that punches into the stratosphere, and if there's a little jetlet, and so you have this type of motion. So this is not forming PV dipoles because the flow speed is weak. So it's more chaotic in appearance. The next example would show that. Okay, so that's a 28 meter per second jet isosurface, and the blue blocks are -1 PV unit. So you can see the tilted updrafts of creation of negative anomalies that hit the stratosphere. And when that happens, you get a boost by a factor of 20 because the one aurora d theta is the aspect of the tropopause. So yeah, this is just very preliminary. Obviously, if we're Shelley might work this up for some kinds of a case study. There's kind of a loose dynamical similarity between this and the Super Tuesday storm, which she's sort of interested in exploring. All right, so here's radar, and I'll speed it up. So this is the first half of the storm. You can see it's starting to set in, and of course Shelley cut it in half, so we have to go to the next. No, I think these are long files. All right. Here's the second half of the radar sequence, which really focuses that precip in western Dane County, Black Earth Creek. So the basic idea is you have a kind of a split jet structure with a warm upglide pattern and thunderstorms breaking out, and that's a key ingredient. Okay, so here's sort of an overall sense of the evolution. And then the last thing for this case would be infrared. So the units are 17. So red is 17 milliwatts per meter squared steradian inverse centimeter. Blue is higher, so it's a little band in the infrared. So red indicates cold cloud tops. And again, this is the first half of the storm leading up to the precipitation in Dane County. So then we'll do the second half. Oop, here we go, starting to get cold cloud tops. Put that out of the way. So I guess a tight little low that was destroyed rapidly, but the thunderstorms just kind of took over. All right, you want to try a little bit on, so Shelley, do you want me to try to explain this numerical modeling dilemma at the moment, or do you want to? Shoot, I lost mine. This is at 12.5 kilometers for PV, and you can see PV dipoles forming. The low PV element is to the left. That's because in strong northeastward mid-tropospheric flow, when a thunderstorm updraft brings that air to the base of the stratosphere, it's got the dimensions of an updraft, which is small. So the spatial scale for taking a derivative to calculate dVdx minus dVy, that really amplifies things to have a small scale structure. So you see the blue is always to the left. I'll stop it. There. Boom. That's kind of a good one. All right, so there's an updraft in here, and it's bringing very fast horizontal moving air toward the northeast. And so there's a jetlet right here relative to the slower moving air at this level, which is 12.5 kilometers. Because there's a jetlet, this side goes that way and that side goes that way. And that's why you have a PV dipole. It took 4 years to figure that out.
Well, that's a vorticity dot.
Yes, and then it's amplified by 1 over rho d theta VC at the tropopause relative to mid-troposphere by a factor of 20. 1 over rho d theta VC at 12 versus 5 kilometers is a factor of 20. So this one's a bit tricky at first. On the 27th, so 1 week later, another huge rainfall event in Baraboo region. This stuff will clear out. That's not really the main stuff. And there's a period of time when it's not raining. And then these things develop in Minnesota. A nice, I guess, gust front. Right. So this is leading up to the time of precipitation.
And I think I recall this one didn't. This one was more like a classic sort of summer convective event, not tied to a
It's spread. Okay, so those guys that were traveling toward the northeast in Minnesota, one of them spread straight east, just barely enough to do this, and so we can see that. Oops, yeah, here. All right. So I don't know if I really understand this one. You're right. This seems different. That there's sort of a draping, trailing front that turns in geometrically, so it's going east-west for a long period of time, and that kind of just loosely explains it. At long tail end of that precipitation event, just went on and on. And this may differ quite a bit from, there was a 2008 event that washed out the road that goes up the Highway 12 that goes up and over the Baraboo Hills.
Yeah, August 2008.
Yeah.
Yeah, that one had more of a direct connection to a tropical depression further to the south. I think.
Wow, these are all fairly different then. Okay, then this is the infrared view of that. Yeah, there's a lot more that could be done, obviously, to look at cross sections and vertical motion fields to try to sort it out. So to me, these two cases confirm the idea of how PV dipoles form. They loosely confirm the general idea that if you have inertial instability, it can promote stronger precipitation. So this is the first half of it, and here it's approaching from the west. It gets kind of impressive in infrared. Okay, this is the last one. The geometry of these cloud top features is radically different than the radar features near the surface.
Yeah.
The linear at the surface, where these are just huge blown out structures that might be hard to figure out from that alone where it's really raining hard. You know? It's not raining hard over that whole patch of red. It is along here, right through here.
Notice that looking at the GOES 16 imagery, it's sometimes hard to reconcile what it looks like from the visible during the day to what it ends up looking like after dark in the infrared, and compared to the radar too. They just don't a lot of times you don't see the bright towers that you think you would see based on either radar or the visible satellite earlier in the day.
Well, so let's open this can of worms. So we'll go back to the UW-AOS simulation. At the end of this, there really isn't any encroachment of that last thunderstorm into southern Wisconsin. It tends to stay north. So this is initialized with 0.5 degree GFS data, and it's run at 10 kilometers. And it's the precip feature is 24 hours after initialization. So there's 24 hours of time where the model can make up whatever it wants, only guided by what's coming in the western boundary. Shelley has been trying, she has a 5 kilometer run pending, but the main thing is to try different initialization data sets because apparently the GFS did take the storm farther north than it actually occurred, and that other model runs might be better for initialization. Don't know. All right, well, thanks for your time.
There's some interesting things there for sure. I mean, that's really
Weird things to think about.
Yeah.
I mostly wanted to show the destruction of that PV anomaly.
That's amazing. I've never seen anything like that because I've never directed my attention to it, but that was really pretty remarkable and very different from the second event where there's no really obvious organized PV structure that's susceptible to that destruction.
Outflow gust front sort of sprawled out into a line and moved eastward.
Yeah, that seems that I remember when it happened, it struck me that it was more, as much as I know about this stuff, which isn't that much, but it was more like the classical summertime convective event than the one on the 20th was. That was definitely a weird event. So that's neat. Thanks, Matt. Well, now we'll transition to a quick discussion of the next big weather event.
Your pointer's over here, John.
What?
If you want the hand pointer, it's over here.
Oh, yeah, I don't think I want the bishop's crook, whatever it's called. Okay,
This is
what do they call it? I can't remember the name.
Shepherd's Crook.
Yeah. Okay, I don't know much what to say about here, Pete. I think we'll skip it this time, just in the interest of time. So let's start with our current satellite data, just for the last day or two, or 6 hours or so. Color, that's fake color though, right?
It's sort of, it's real red and real blue and a green that's made up from a channel that's really sensitive to chlorophyll.
Oh,
So it's effectively looks like what it would look like.
Oh,
Very
that's pretty
close.
cool. All right, so here's our satellite movie for the last 6 or so hours, and there's a few features of interest. One that I'm going to dedicate most of the rest of the discussion to, and that will be the feature that you can't really see so well in the cloud mass is a big cloud mass over eastern Canada, and maybe a bit of a dry slot over sort of northeastern Michigan, and that's tied up with the development of maybe the first really powerful extratropical cyclone of the season over North America. And we'll say a little bit more about that as we move forward in the forecast. Trailing to the south of that feature is a band of cloudiness. Yesterday was raining along much of this. We'll see on the radar in a minute. There's still precipitation along some portion of this trailing cold front. And that was the feature that kind of came through us late last night, early this morning, and had fizzled a little bit, but not entirely. Greg had 1/4 of an inch. I probably had the same at my house, so if I don't measure it, I should. A number of us don't have rain gauges. We probably should. But anyway, my cats are being it too, just like these, I think. And then there's a swirl just to the southeast of Bermuda that looked a little bit more convectively active yesterday, but didn't look less swirly than it does today. So this is a very interesting vortex structure. And I don't know if there's any interest in that from the Hurricane Center.
Is that what's left over from Florence?
I don't know if that's true or not. I mean, Florence kind of got stretched out over New England. It rained there earlier in the week. I just don't know if that's the same.
It looked like it might have had something to do with the lower level vortex part of it is
Okay.
left down there.
Okay, that might be
That's
true.
what that is.
And then it's very cold over the North Atlantic. You can see all this open cellular convection south of Greenland. There's a disturbance in the immediate coastal region. And here's flow off the continent or the island, and it's clear there. It's really nice on this picture. You can see a lot of nice things there. Okay, let's take a look at the radar across the continental U.S. next. And here's some of what was left over from, you can even see on the front edge of this, this is what was kind of coming through us late last night or early this morning, and it's kind of been completely decimated. a few convective elements in southern Indiana still around, and then the more widespread precipitation over almost the entire state of Oklahoma and parts of Texas. On the far southern fringe of this is probably related to some other disturbance entirely. We may see that when we go to the upper level charts. So what's happened in the wake of our frontal passage precipitation last night is finally a decrease in temperature. Yesterday was brutal in the afternoon. 90 degrees almost, I think it was 87 maybe when the sun came out, and the dew point was 72 when I left work. I'm glad that's over. And it may be over. Huh?
Did you see last night at midnight it was 80 degrees?
I knew it was 82 at
It was
10.
very
It was
nice
80
in the
degrees. That might be the highest midnight temperature we've ever had this late in the season. I bet you that's not
That's what I was contemplating as well.
I wonder if it isn't. And one would have to go through all the options to verify, but I think you could probably convince yourself that that's the case. That was brutal. So I'm glad that's over. And we'll see colder air to the north poised to make maybe 1 or 2 excursions, the second of which a week or so from now may be more impressive. So I'm looking forward to that, as you might guess. Okay, let's take a look at the surface ops, Pete, if we could, on the big surface map. So yesterday, as I said, it was, I think the high was maybe 85, 86 in the late afternoon when the sun had come out, but the dew point I know was 72. Now it's 51. Now that's a comfortable, respectable dew point, if you ask me. And you go further south where the flow is still southerly, like near Nashville and other parts of Tennessee, southern Illinois, 73 dew point down near Marion, Illinois. Indianapolis is 68. It's probably 70-ish in Bloomington. So it's not comfortable to the south, and that's about where the leading edge of the few echoes that exist are currently situated. And you can see a little bit of rain here in Erie, and then, not surprisingly, somewhat scattered, but 89 over 69. Raining with no clouds in the sky in Erie, Pennsylvania. So you're somewhere near a smokestack or something, that's what I'm guessing here. But anyway, generally, that's the boundary of where the really moist air is and the really uncomfortable air, and we're finally been ventilated by some relatively cooler air. And it was windy this morning. It still is, actually. Around the region, winds are not, it's not so uncommon to find a 20-knot sustained wind, like we see over much of the central part of Iowa, parts of the near La Crosse. Milwaukee's at 15. We were certainly 15 to 20 earlier, and Green Bay's at 20. So that's with the sea level pressure minimum. Let's see if we can find it quickly on the map. Maybe somewhere up in here, right? So something like 986 or so up here in southern Ontario. So somewhere in this location is the center of the low pressure. It's somewhere in the mid 980s for sea level pressure. And it's going to get a lot deeper over a period of the next day or so as it moves to the northeast. Okay, let's take a look at our upper level charts, Pete, the super Pete's, and we'll start at 500 millibars. Here's our map this morning at 7 a.m. It's really a beautiful wave structure across the eastern 2/3 of the country. So I'm kind of dividing everything from here to the east. Here's a sharp upper wave over the Minnesota-Iowa border. Wind speed at Minneapolis is 65. It's 80 at Green Bay. It's 65 down in Moline. So a really nice little jet at the base of this trough. So there's not only curvature-induced tendency for a subgeostrophic flow here, but there's also going to be ageostrophy resulting from a long flow speed change, which is not insignificant at this level. Not only that, pretty nice little temperature structure associated with this thing, even at 500 millibars. So there's pretty strong cold advection across southwestern Minnesota in cyclonic shear. That's probably depressing the tropopause and enhancing the chances that a more robust upper disturbance will begin to develop out of this trough and then spawn cyclogenesis downstream. Not only that, this trough axis is in fairly close proximity to a pretty robust little ridge over maritime Canada. And so I think over time, we're going to see a little bit more concentration of this trough ridge couplet, and that only enhances the curvature-induced ageostrophy. So there's plenty of reasons to expect divergent motions in the atmosphere over far southeastern Ontario and around this time. And that's just about where we're seeing, we saw just a minute ago, 986 millibars in about that location. And this is a development region, not just a region of already, a finished development. So very interesting structure. Let's go to 300 millibars before we go lower.
I point out there's that vortex in the Oklahoma Panhandle. You know, you can kind of see it in.
Yeah.
And I wonder what that is. I mean, is that
No.
a tropical one?
I don't know. We saw that kind of region of precipitation over the whole state, just in the radar. So I don't know. Maybe it's partly a function of heating that's been sitting there. It's a good question. I don't know. But it's its own separate disturbance. It doesn't show up so obviously in the geopotential hype. I'm glad you pointed it out, because that's the signature of whatever it is that's inundating Oklahoma right now. Very good point. Maybe we'll see some other things at lower levels or higher levels that might clue us in. But let's start at 300. So here's our 300 millibar ice attacks. It's a fairly complicated structure today. I verified earlier, and I won't show everybody today because it takes a little more time. This is really a subtropical jet. It's probably not surprising to any of us in the room that the whole continental U.S. in the eastern half at least has been under the influence of tropical sort of air masses for the last week or more. And this is the northern boundary of that tropical boundary. So that's a subtropical jet. And sort of heresy. We're live streaming. Somebody's going to say, "What are you talking about? Subtropical jets in northern Canada?" But that's central Canada. Sorry. I got Greg Tripoli on my side, so I feel pretty good about that. Here's a little jetlet that's got a little bit more potency than I think I expected from yesterday. Maria, you probably agree. This thing looked like a little
I was just looking
weak
at
jet, didn't it?
looking at yesterday's compared to now, because it looks a lot stronger.
Yeah, this is 139 knots, and these are observations now, so it's 139 right at Minneapolis. So this is a strong jet at 300 millibars. And yesterday, I think we were expecting it might be in the 90 to 95 knot range. So that thing's blown up a little bit. And that's interesting. Very strong baroclinicity associated with it as well. And let's see, it is getting colder here. So again, we're not in the tropopause, or not in the stratosphere at 300 millibars. So it's getting colder where it should on the cyclonic shear side of the jet axis. Let's try and let's see what it looks like at 200 millibars speed. At 200, this thing is much stronger. So see, that's why it's pretty clear it's a subtropical jet. It's 172 knots at 200 millibars, and it's less well organized anyway as a jetlet across Minnesota, Wisconsin than it was, and the wind speed at Minneapolis is only 110 knots. So you're above the level of maximum wind at 200 millibars. In this location, it's lower down.
I think the tropical plume is all focused in that ridge on the east coast. And
This thing here.
the tropical plume is pushing up perpendicular to that. That's what's pushing that jet on its front side. But the back over there in the west, there seems to be nothing from the tropics pushing up too much on the western side.
Yeah,
of the west.
that's for sure. And this is a weak feature as well, but it's definitely the case, yeah. In fact, if we go lower, let's go to 850. I think we'll see what's poised and waiting. We could have seen it at 500. This is very cold air over the northern and central Canada. So with the lowest observed, or lowest observation is -12, the analysis puts -15 just a little bit to the west of the western shore of Hudson Bay. So that's really cold for this time of year at 850 millibars. Here's the geopotential height disturbance associated with the cyclone in southern Ontario. And it's got a robust set of baroclinic zones with it. Really looks like the first autumnal storm of the year. There's a pretty decent temperature contrast. I think still yet to be organized in a better fashion than currently, but that's a baroclinicity we haven't seen yet this year, except it was draped across central Canada earlier this week and waiting for something to come in and kind of organize it. And here's the disturbance. So pretty decent uniform an air of uniform temperature in the so-called warm sector, and then suddenly there's pretty decent warm air advection and clearly differential temperature advection because there's a trough feature there. Remember on the satellite, we saw a wide region of clouds. We don't get much radar information even from southern Canada, which is unfortunate, but I suspect it's raining under a large part of that cloud mass in Ontario and parts of Quebec, and that's in a warm frontogenetical region for sure. Look at this 90-degree wind shift. They're not exactly at the same longitude, but one gets the impression that the flow is over here in southeastern Ontario is from the same direction as it is here in Quebec. And then you go to the north of James Bay, get an easterly wind. So there's really strong warm frontogenesis going on there. And then there's differential cold air advection going on back on the western side of the storm. And there we are in Madison, beneficiaries of cold advection. It's getting cooler as the day goes on. Dew points should continue to drop. So these are all good things after the last couple of weeks, especially after yesterday's real spike, which was not comfortable. And then Greg, we don't really see the same exact type of signature of a
Not really.
minimum, but there's a little bit of a low geopotential height feature down near Lubbock, which perhaps, let's imagine it's displaced a little and you move it further toward the Red River and you're not that far off from where that precipitation is over Oklahoma. So I want to say a few things about the current or near current state of this
You know, I
disturbance.
think part of the problem there is
Yeah.
850 millibars is sort of cut off on the western side of that because of the elevation.
Yeah, that's right. These are all.
So
here's
we
a good
may not, the
example.
winds may be so affected by friction there, you have to go up to. 700.
Yeah, could be. We have 700?
That's
Yeah, so here's the structure that you can see. This is a little bit more obvious of a structure, isn't it? And then here, even though the temperature advection per se is not strong, it is positive and somewhat non-uniform. So that might have something to do with what's going on over Oklahoma. So there is a separate upper disturbance in the middle troposphere, not the lower or upper troposphere, that kind of maybe has something to do with what we saw in Oklahoma. And then look at how the baroclinicity gets itself even better organized in the middle troposphere. This is really nicely put together. It's right where the geopotential height trough is. So strongly frontogenetic here. 0 at 700 millibars here. So it's warm enough to be rain everywhere. And then we're still in the very nicely organized cold advection region on the upstream side of the geopotential height minimum. So we should get colder as day goes on. And as starts to happen sometimes in these nice developments that are close to us, cold advection and southwesterly flow at Green Bay. That's not uncommon when you're on in the midst of a nice development that's going on. So really interesting day today, I think, for us. So let's take a look at a couple of,
It's also interesting that it's on the 21st of September.
which is the last day of summer.
Yeah,
Yeah, tomorrow at 5 p.m. is
it's like we can visibly see fall moving across the map.
Yeah, that's right. Yeah. In fact, if you take the 0 degree isotherm at 850, wherever that is, it's already fall. That's what somebody told me a long time ago. I think it was Jim Moore, I'd say it was you. So we have several states, Minnesota, the Dakotas, and most of Montana, already fall. So it's right about here. Let's go, Pete, if we could, to, I think we'll go to the Omega page first, if we can do that. That's the new one too, isn't it? Yeah, excellent. Okay. Let's do it at 0Z because I like to move a little bit into the forecast. So here's a 700 millibar quasi-dystrophic omega for this morning at 12Z. And remember, at that time, we had our surface cyclone just about here in southeastern Ontario. And so the yellows are regions of ascent and blues are regions of descent. And then the thickness from 500 to 900 millibars is dashed white. So I hope you can see all of that on there. So there's a nice couplet of updraft and downdraft associated on the broad scale with the wave structure we just saw at 300, 500, and even 700 millibars. And so remember, there was a nice trough axis right along the Wisconsin-Iowa border, and then there's a ridge axis over Quebec. So in between the trough axis and the ridge axis is where there should be upper divergence and nice ascent, and upstream of the trough axis is where the descent is. The cool thing about this is that if we go to another portrayal, let's first go back, Pete, let's look at just the Sutcliffe form of this. So this is an approximation that leaves out the so-called deformation terms. And so it looks a little more impressive, but the broad structure is the same. A nice updraft at the base of Hudson Bay and then a downdraft over sort of Sioux City, South Dakota. And so this is all vorticity advection by the thermal wind in the layer from 500 to 900 millibars that's producing this vertical motion. If we split the vorticity into shear and curvature, noting that we saw the jet was well to the north in our case, except for that little feature over Minnesota, and there was really abundant curvature. Let's see if there isn't some distinction between those two pieces of this total forcing. So here's the shear vorticity forcing, valid at the same time, same level. And near the cyclone center, let's say 1, 2, 3, 4 microbars per second of ascent, right about there. Let's go to the curvature vorticity advection by the thermal wind, which is right there. And so at this time, it looks like the shear is doing a better job of forcing the air to rise in that location of the cyclone center. Now, let's go ahead to, I think, 36 hours. Let's go to 24 first. Let's do that. So we'll do this one first, Pete. So here's the total Sutcliffe forcing. The storm is propagating to the north and east, pretty intense updraft, split into two cores, but I'll say this one might be the one that's going to be the more intense between the two. Let's see what this looks like in the shear vorticity advection at 24 hours. And this looks a little more anemic. So now we're only about 4 microbars per second at this time. It has the same dual maximum structure, but let's see what the curvature looks like at this time. And the curvature has the dual maxima, and so they have roughly the same magnitude. To my eye, this is spread out a little bit more, and so if I'm thinking about trying to generate a vortex by column stretching, I want to do that with the most concentrated amount of updraft. So maybe even at this time, the shear is going to do a little bit more height tendency in the lower troposphere. Let's go to 36 hours, because I think it changes. So first, with the full PVA by the thermal wind, there's a really intense updraft just about to get into the Labrador Sea. So this is really an intense cyclone. You'll see in a minute how intense it gets. And then let's go back and take a look at the two pieces of this forcing for the fun of it. So this continues to look anemic. This is the shear vorticity advection by the thermal wind. And now how about the curvature? Yeah, the curvature starts to take over. So the curvature in the flow begins to be the dominant mechanism by which, at least this diagnostic mechanism, by which you're taking the air out of the column right in the vicinity of the cyclogenesis. So there's something interesting about almost every storm has some ability, some sort of transition between these two pieces. But this one seems to have been more dramatic than ones I've seen before. Maybe it's just because I was paying attention to it over a period of days. But suddenly, near the end of this evolution, the curvature is the main driver of the upper divergence. And let's see if we can't see that by first going to some upper level forecast charts, 500 millibar charts. Remember, that's the 36 hours initiated last night. So if we use the 0 hour forecast, we'll be looking at the same thing, even though it's now old. So let's go to 500 and start at 12 hours, which is I think where we started. So here's our wave structure that we just saw on the observation map. So here's the trough axis over the ridge axis over maritime Canada. Really nice looking trough axis right to our west. And so there's the separation between them is some, sizable distance. Let's go now to 24 hours in the forecast. A time at which there was no discernible change in the, curvature versus shear contributions to the cyclogenesis. So here's the trough axis, but it's kind of elongated. It's not really got the same structure it had before. Distance is a little bit smaller between those by eye. And then let's go to 36 hours. I think it looks different then, although it's still a hard storm to figure out, in my opinion. So here's maybe the trough axis, and the downstream ridge looks a little bit closer. And so this is at least in line with the notion that the curvature in the flow is driving perhaps more of the divergence than anything that has to do with the long flow speed changes or shear. So let's take a look at, for the fun of it, we don't have to go anywhere else. We can tell about the shear here. The shear here is not so strong, but the curvature is considerably stronger at this particular time. That's what I meant to say. So this is a really interesting storm, and not so easy to diagnose. I don't think it's very easy to diagnose. And we have this little strip of what turns out to be, you can't see the scale, but this is negative absolute vorticity. So Matt, this is just like what you're talking about, that you're taking air that's got really poor stratification from the boundary layer, injecting it into the upper troposphere, and it produces that strip of inertial instability. So if there's air that's being compelled to move one way or the other in a squall line, it's going to have an easier time getting out of it. Let's just see for the fun of it at 36 hours if there's a heavy precipitation line there. Sure is, right there. So they're tied together. This is very commonly the case. And there's our storm, 967. Remember, at 7 a.m. this morning, just 24 hours before this time, 985. So this thing's dropped nearly 20 millibars in a day. It's a really intense development, and the first really good one of the year. It's not actually done at this pressure level. It gets lower than that.
That's lower than yesterday too, isn't it?
I think so. It's bounced.
972.
Yeah, it's bounced back and forth in terms of its intensity. Today is more intense in this short-term forecast than yesterday's short-term for roughly the same time. There's so many interesting things about this storm. The rapid development is one of those interesting things. I'm really always intrigued by that. the fact that the precipitation spine is right along the axis of strongest local warm advection is very interesting. There's no warm front effectively on this storm. Look at how the thermal the thickness lines have no particular concentration. There's no structure to the eastern side of this thing thermally. So there's no warm front. There's a very strong cold front. Such warm frontless storms occur quite often, but I don't know if they're different and in what way they might be different from storms that have a much better organized, obvious warm frontal structure. And those tend to also get a more organized, occluded structure later on in their life and precipitation hanging back in the occluded sector of the northwest quadrant of the storm. This one doesn't have that. So it's very interesting. It's worthy of investigation, I think. The other thing that's neat about it is in its wake, beautiful anticyclonic conditions settle in over us. This is valid Saturday morning. The high is sitting just about right over my house. The thicknesses are in the 558 range, so that's a high of about 60, dew point of 8, no, maybe 55. Beautiful day, beautiful fall day. And look at, here's another one with colder air. Look at that thickness, 509, right there on the border between Manitoba and Ontario. So that's cold air. And here's an anticyclone. We were talking about this in 452, the Sutcliffe 1939 paper on development. It's much easier to watch anticyclones move in the direction of the thermal wind than it is cyclones, because the cyclonic circulation distorts the thermal field to a great degree. The anticyclonic circulation does not, because it's weaker in the middle than it is on its periphery. So in the middle, the thickness lines go straight through this thing. So watch where this cyclone goes next. The Sutcliffe theory would suggest it heads toward Lake Winnipeg in the direction of the thermal wind. Let's go ahead, 12 hours, Pete. There it is. Let's go ahead 12 hours more. It's probably going to be somewhere in here if that theory holds any water. There it is. So it keeps on moving in the direction of the thermal wind. Cyclone's down to 955 now, just 24 hours later. So it keeps getting stronger. It's on the western side of Greenland, right at the mouth of Labrador Sea. So very intense cyclone. And so the parade of anticyclones in the wake of this broad circulation puts us in a position to really enjoy some nice autumnal weather. Just a little bit too warm for snow across southern Manitoba, southern Ontario, and northern Minnesota, the Arrowhead region, and parts of Lake Superior. So it's going to be 39, 42 degrees and raining in some of those places, likely, by the time you get to Sunday morning. So it's really, really nice weather. I want to do one last thing, if I can, and that's look a little bit at the distinction between the influence of curvature on the flow and the influence of a long flow speed change. Kate Abbott's going to work on this problem in some detail, and this will require GEMPAP. So if you can go GD plot and then restore along _ AGO, and then we can run that. So here is a picture of the 500 millibar geopotential heights in a 24-hour forecast. This is honest 24-hour forecast from last night, so it's valid 12 hours from now, so tonight at 7 p.m. And then I'm showing you in blue the ageostrophic winds, the component of the ageostrophic wind at every grid point that is along the actual wind. And the reason I'm doing that is because if this is a wind vector, right, and so this is the head of it, it's nice that's there. And if I want to change its direction, I have to tug it in either that way or that way. Perpendicular to its current state is the only way I can change its direction, right? And if I want to change its speed, I have to do something in the along flow direction. And those somethings have to be accelerations to change one or the other component of the vector, magnitude or speed. And if you take the vertical cross product of acceleration, you get the ageostrophic wind. So if I'm thinking about the direction change, and I take the vertical cross product of something that's perpendicular to this, then that resulting vector is going to be along the flow. So that's why I'm looking at the ageostrophic winds along the flow, because these are the ones that are influenced by curvature, and it's just at this one level. So you can see by eye, here is some strong counter-flow ageostrophy, and it crosses the geopotential height lines because I'm not making it along or across the geostrophic flow, but the actual flow. So there's subgeostrophy in the trough, and then there's supergeostrophy in the downstream ridge. And in between is where you get your upper divergence. So let's take a look at the next thing you can put in here, Pete, is restore DIV _along AGO. And all that does is going to put the divergence of that wind field on top. So here it is. So here's the upper divergence in units of 10 to the minus 5 per second. So a broad region of upper divergence, exactly where you'd expect it to be, downstream of the upper trough and upstream of the downstream ridge. And if we walked this through time, you'd see the influence of curvature would end up giving you this divergence of these two separate pieces. And you'll end up with the most fundamental partition of the vertical motion field that you can get. You're appealing directly to the only two things that can accelerate the flow, or the only two aspects of acceleration that matter are speed change or curvature. So I think we're going to have some fun doing that. And here's an example of some of the insight that might be gained by doing this in a systematic basis. Okay. And I could show you the cross flow agiostrophy and its divergence, but as you might guess, with the jet farther to the north, it's not going to really be a big factor at this time in the storm, and it wasn't. So that's why I'm not sure. So can we do one last thing, Pete?
Yep.
And that is, we'll go to 850 millibars in our, we've got to go to a longer forecast. Let's just watch what happens at 850 over the next, 10 days or so. Because we're about to see a pretty big change at 850 millibars. And we can use the 12 in the forecast. If it's in, it might not be in.
It's out through 384.
Okay, so let's take a look at the loop, and we'll just jump ahead every couple of 12 hours or so. And we're going to stop at the beginning. Okay, thanks. So here's the current, this is 12 hours valid tonight. So here's one pocket of cold air. And this is the big cyclone that's getting revved up and headed toward Labrador. And we have cold advection behind us. We're certainly getting colder. I think this is 0 degrees at 850. So let's go a couple of clicks forward and watch what happens. Here's our big circulation. It seems to ingest this cold air, gets it about to the border, and that's about as far as it goes. So we warm up maybe a little bit after that. That's for Saturday night. Keep on going. And the cold snap, that first one disappears, is kind of modulated by coming further to the south. We're a little bit warmer than we were. Keep on going. That's Monday. Here comes another cold air mass sliding southward from the pole, another cyclone to our north and west by about early part of the week, Monday night. And there goes that storm. And in its wake, I think that's what opens up the floodgates for some of this chillier air. And at the same time, there's what looks like a little Alberta clipper developing there in northern Alberta province. So let's go forward from Wednesday. Here comes that thing southward towards us, and it's going to end up over us Thursday morning, Thursday afternoon. And then look at that. Look at that intense wind speed maxima on the western periphery of that cold air mass. Gets me nervous, or actually excited. Temperatures are about 0 in the blue, and you get below 0 at 850 into the darker blues. And now it's invading. So here's fall, Greg, over the Great Lakes states a week from today. Let's see what happens next. That storm takes the same path, although with less intensity as the one before it. Colder air settles in a little further south, but I bet it doesn't quite get all the way down to us.
Tropical cyclone.
Yeah, there's another tropical disturbance. Another tongue of cold air. So this is why Kalispell and places like that are always so cold, because they're the first ones to feel these polar air masses, even when it's late September. So this is Sunday morning, and we're still, we've got a little bit warmer, but we have a frontal boundary coming through us on Sunday morning with this next storm. It's a very active period for us. And then it gets downright cold to begin October. Let's go back one click, I think. Yeah, look at that. That's minus, I can't read the number, but -4 to -6. That's downright cold air sitting right on top of us, 12Z Monday morning, the 1st of October. And then that's the worst of it that's the worst of it. So then it's a gradual warm up by the end of that week, it looks like.
So we could get our first frost.
We could get our first frost.
So it would be an Indian summer then.
Yeah, after October 1st, any warmth is a different category. That's right. So this thing that went through last night dropped our dew point from 72 to now 55. That's the beginning of the end for the summer. It's very obvious. And they may be, warm afternoons and times where you feel, oh, wow, this is really nice weather after the last 2 cold days. Nothing's going to be bitterly cold, but everything's going to be dry from here on out, it looks like, in terms of dew points. I don't know how many times we're going to get those dew points near 70 again. Maybe this will be one of those episodes, but it's going to be after perhaps the first frost around the end of the month, 1st of September. So things are changing.
A requiem for mosquitoes, but not.
Yes, that's what I can't wait for. I need that temperature to be 38 degrees or colder one night to just kill these damn things. Either that or somebody please tell me what role they play in the ecosystem. I don't have any idea what it is, and so I can't be on their side.
Aren't they bat food?
Yeah, but we can give them something else. I'll do something else for those guys. I just hate the mosquitoes. So anyway, it looks like they may be meeting their doom in the next week or so. So that's all I have. Pete, thank you for driving. Matt,
Yeah,
Shelley,
we
thanks so
do
much
have
for
a-
your interesting stuff.
Somebody online, Dave Demuse, one of our alumni,
Oh, yeah.
says, if there's time and anyone's interested, the UK was just hit, maybe Luke, you know something about this. UK was just hit with a massive windstorm. BBC reports 100 miles per hour from a very deep low pressure system that's now over the North Sea.
Was that Hurricane Helena?
I wonder,
Originally?
I think it might have been remnants of one of the tropical systems. But
Yeah,
it was called Cyclone Alley, I think.
Okay.
The first one, they actually got hit by another one. I want to say it was Donald. I don't know what the second one was, but that one hit Southern England, so.
I think last week when we were watching Florence, Helene was out in the middle Atlantic, and I think it was making its way toward the British Isles. It was the only one that was doing so. And I think it was kind of potentially phasing with some other disturbance in the polar airstream. That might be what it was.
I think Northern Ireland recorded its strongest September gust ever.
Is that right?
91 miles an hour.
Wow, that's amazing. So that's not unlike the October '87 storm, because that's what happened. It was a tropical disturbance that got involved in the extratropics in a serious way. So let's see if we can find anything about this. 8 hours ago, it's going to hit Britain. So is this the same one?
No, that was one that hit Southern England.
this is old. September 21st.
Yeah. So this is
Probably a new one.
a new one, because you said the first one had a name Alley.
Yeah.
So I guess maybe if you look for Storm Alley or something, ALLY, we gotta stop naming these things.
It's AL.
Yeah, ALI, I guess. Oh, there's the one, yeah. Winds last UK and Ireland.
Did I get the wrong one?
Whoa, look at that.
It's the guy from the
100
Weather
mile per hour
Channel.
strong winds. He's on the cliffs of Moore too, 700 feet to the Atlantic Ocean. You don't want to do that. You know, somewhere else. Be on a golf course or something, you know? You don't want to be on the cliff. Wow, look at that. Why these storms
There
have
you go. Why
names?
does it have names?
It's a good question, but we're not going to entertain that today. But wow, look at that. Yeah, there's a lot of this happened in '87. A lot of those big trees went down, 300-year-old oaks and so on. Yeah, so I'm sorry we didn't have time to look at this with weather maps, but that's certainly something to pay attention to. I think these ferries have a little bit higher profile for where they operate, don't you think?
This one got dragged.
9 stories high.
With 500 people in it.
Yikes.
It's just terrible.
It's like wind texture for sure.
Oh, maybe there's a satellite embedded here. Okay. Get out of the way.
They're gonna be sound hooked up for this, so we'll have to read those.
Chris Fox, he's not related to Guy, right? I don't know if he is or not. The Highlands, I'd love to go to the Highlands. Anytime from October 1st to January 1st, I'm there. I would love it. Look at these places.
It's windy pretty much all the time.
All the time, yeah. They can get up to almost 200 miles per hour.
They report their winds in miles per hour in Britain?
Yeah.
I thought they were on the metric system.
Didn't we get the?
They put degrees C on their maps, but they use miles per hour, I guess. All right, so let's see, this was Thursday.
I think this is the next, that was the next system.
Okay, yeah, we're not seeing anything more. We're done. Thanks, Dave, for tuning in.
Thanks, Dave.
We did what we could to pull this stuff back from the UK there, to keep that stuff from us. I don't know why, but. All right, we'll be back next Friday. Thanks everybody for coming. Again, thank you, Pete, and thanks, Matt and Shelley. Very interesting stuff. I hope we see more of it. Thanks.
So you're a junior this year?
Yeah.
Is this all like a lot to deal with?
Oh, absolutely.
I understand.
People are bringing ED